Let's fucking go, buddy. Welcome in, everybody. How you doing? Back with another episode of Aviation Prattle. Let's fucking get it on, buddy. Let's get it on. Today's episode is the SR71 Blackbird. The amazingness. Everybody fucking loves this thing. Everybody fucking loves this thing. Let's go. It's fucking awesome. It's the IRL spaceship is basically what it is. The fact that we didn't really pursue anything past this, and we retired it. At least that the public is aware of. I'm gonna go ahead and throw that out there. At least that the public is aware of. Right? Like, yeah, we retired it, but I like to think that we pursued something beyond this. The Aurora project. Maybe I'll go over it one day. Maybe not. No, I'll probably go over it one day. It's actually really interesting. Obviously, I'm not going to have any video footage of it, because I don't think it was ever completed. And if it was, well then fuck. I guess I was wrong. But that's not today's episode. Today's episode is the SR71 Blackbird. A retired, long-range, high-altitude Mach 3 Plus strategic reconnaissance aircraft developed and manufactured by the American aerospace company Lockheed Corporation. Fucking legendary, let's go. The SR-71 was developed as a Black Project reconnaissance aircraft during the 1960s by Lockheed's Skunk Works division. Initially, as a bomber variant of the Lockheed A-12 requested by Curtis LeMay, before the program focused solely on reconnaissance. Yeah, it was originally intended to be a high-speed, like, can't touch this kind of bomber. But, alas, going fucking a mile every 2 seconds makes your shit have to be pretty on fucking point. Your mathematics have to be next to perfect to hit anything. And then there's a lot of variables to account for and shit like that. But anyways, American aerospace engineer Clarence Kelly Johnson was responsible for many of the aircraft's innovative concepts. The shape of the SR-71 was based on the Pioneer Stealth Lockheed A-12 with its reduced radar cross-section. But the SR-71 was longer and heavier to allow for more fuel and a crew of 2 in tandem cockpits. After the SR-71's existence was revealed to the public in July 1964, it entered service in the United States Air Force in January 1966. In 1989, the United States Air Force retired the SR-71 largely for political reasons, although several were briefly reactivated during the 90s before their second retirement in 1998. NASA was the final operator of the Blackbird, using it as a research platform until it was again retired in 1999. Yeah, they brought this motherfucker back 3 times. During missions, the SR-71 operated at high speeds and altitudes, Mach 3.2 and 85,000 to 92,000 feet, allowing it to evade or outrace threats. If a surface-to-air missile launch was detected, the standard evasion action was to accelerate and outpace the missile. Shit. Mission equipment for the plane's aerial reconnaissance role included signals intelligence sensors, side-looking airborne radar, and camera. On average, each SR-71 could fly once per week due to the time required to prepare it for the next mission. A total of 32 aircraft were built, with 12 lost in accidents and none lost to enemy action. However, there was one time a Swedish J-37 Viggen got a confirmed radar lock on it. We went over that in the last episode, and that is why we're covering the SR71 today, because it was brought up last week. Since its retirement, the SR-71's role has been taken up by a combination of reconnaissance satellites and unmanned aerial vehicles. A proposed UAV successor, the SR-72, is under development by Lockheed Martin and scheduled to fly in 2025. That's next year, fellers. Are we ready for that one, the SR-72? Oh, shit. In 1974, on 2 separate flights, the SR-71 set the record for the highest sustained flight and also the fastest flight time between London and New York. In 1976, it became the fastest air-breathing manned aircraft, previously held by its predecessor, the closely related Lockheed YF-12. As of 2024, the Blackbird still holds all 3 world records. Still hasn't been beaten. Man, made in the 60s, 2024. Shit. We're 60 years. 60 years after the development, 2024. 1964. Fucking still haven't broken the records, bro. What the fuck? Lockheed's previous reconnaissance aircraft was the relatively slow U-2, but that thing still flew fucking high as fuck, too. Designed for the Central Intelligence Agency. In late 1957, the CIA approached the defense contractor Lockheed to build an undetectable spy plane. The project, named Archangel, was led by Kelly Johnson, head of Lockheed Skunk Works, until the unit in Burbank, California. The work on the Project Archangel began in the second quarter of 1958 with the aim of flying higher and faster than the U-2. Of 11 successive designs drafted in a span of 10 months, A-10 was the front-runner, not the A-10 that you're familiar with. Not the A-10 Thunderbolt 2. Okay? That hasn't happened yet. Calm down. Despite this, however, its shape made it vulnerable to radar detection. After a meeting with CIA in March 1959, the design was modified to have 90% reduction in radar cross-section. The CIA approved a US $96 million, or $758 million in 2023, contract for Skunk Works to build a dozen spy planes. Named A-12 on the 11th of February 1960, They were the... Damn it. Hold on. CIA approved a $96 million contract for Skunk Works to build a dozen spy planes named A-12 on the 11th of February 1960. Okay. Don't know what the fuck has been up with my goddamn reading ability for the past, week or so, but it has been off, man. Holy shit. Maybe I need more coffee. It needs more coffee. But then there's brandy in this coffee, so that might actually fuck my ability to read up. The 1960 downing of Francis Gary Powers U-2 underscored the aircraft's vulnerability and the need for a faster reconnaissance aircraft such as the A-12. The A-12 first flew at Groom Lake, Area 51, Nevada, on the 25th of April 1962. 13 were built. 2 variants were also deployed, including 3 of the YF-12 interceptor prototype and 2 of the M21 drone carrier. The aircraft was to be powered by a Pratt & Whitney J58 engine. But J58 development was taking longer than scheduled, so it was initially equipped with a lower thrust Pratt & Whitney J75 to enable flight testing to begin. The J-58s were retrofitted as they became available and became the standard engine for all the subsequent aircraft in the series. A-12, YF-12, M-21, as well as the SR-71. The A-12 flew missions over Vietnam and North Korea before its retirement in 1968. The program's cancellation was announced on the 28th of December 1966 due to both budget concerns and because the forthcoming SR-71, a derivative of the A-12. The SR-71 designation is a continuation of the pre-1962 bomber series. The last aircraft built using the series was the XB-70 Valkyrie. However, a bomber variant of the Blackbird was briefly given the B-71 designator, which was retained when the type was changed to SR-71. So that's how it's got its name. Or at least its, designation, right? During the later stages of its testing, the B-70 was proposed for a reconnaissance strike role with an RS-70 designation. When the A-12's performance potential was clearly found to be much greater, the U.S. Air Force ordered a variant of the A-12 in December 1962, which was originally named R-12 by Lockheed. This U.S. Air Force version was longer and heavier than the original A-12 because it had longer fuselage to hold more fuel. The R-12 also had a crew of 2 in tandem cockpits and reshaped fuselage. Reconnaissance equipment included signals intelligence sensors, a side-looking airborne radar, and a photo camera. The CIA's A-12 was better photo reconnaissance platform than the U.S. Air Force R-12 since the A-12 flew higher and faster, and with only a pilot, it had room to carry a better camera and more instruments. The A-12 flew covert missions while the SR-71 flew overt missions. The latter had U.S. Air Force markings and pilots carried Geneva Convention's identification cards. Let's fucking go for GCI cards, bro. Gee, fuck. We haven't gone over those yet. We will, don't worry. We'll get over the Geneva Convention identification cards. Those are interesting. During the 1964 campaign, Republican presidential nominee Barry Goldwater repeatedly criticized President Lyndon B. Johnson and his administration for falling behind the Soviet Union in developing new weapons. Johnson decided to counter this criticism by revealing the existence of the YF-12A U.S. Air Force Interceptor, which also served as a cover for the still-secret A-12 and the U.S. Air Force reconnaissance model since July 1964. U.S. Air Force Chief of Staff General Curtis LeMay preferred the SR, Strategic Reconnaissance, designation, and wanted the RS-71 to be named SR-71. So now you know what the SR stands for, right? It's part of the reason I kind of wanted to go over this part specifically, is so everybody is aware what SR stands for. It's not fucking Super Rocket. I've seen that like 50 times. And I'm like, dude, it's not. SR does not stand for Super Rocket. It stands for Strategic Reconnaissance. I'm going to say that again. SR stands for Strategic Reconnaissance. Fucking A. Before the July speech, LeMay lobbied to modify Johnson's speech to read SR-71 instead of RS-71. The media transcript given to the press at the time still had the earlier RS-71 designation in place, creating the story that the president had misread the aircraft's designation. To conceal the A-12's existence, Johnson referred only to the A-11 while revealing the existence of a high-speed, high-altitude reconnaissance aircraft. In 1968, Secretary of Defense Robert McNamara canceled the F-12 interceptor program. The specialized tooling used to manufacture both the YF-12 and the SR-71 was also ordered destroyed. Production of the SR-71 totaled 32 aircraft with 29 SR-71As, 2 SR-71Bs, and the single SR-71C. The SR-71 was designed for flight over Mach 3 with a crew of 2 in tandem cockpits. It was extremely important for the pilot and the reconnaissance systems to offer RSO to work well together as a crew. With RSO operating the surveillance systems while navigating the mission flight path. The SR-71 was designed with the smallest radar cross-section that Lockheed could achieve, an early attempt at stealth design. The aircraft were painted black. This color radiated heat from the surface more effectively than the bare metal, reducing the temperature of the skin and thermal stresses on the airframe. The appearance of the painted aircraft gave it the nickname Blackbird. Titanium was used for 85% of the structure, with much of the rest being polymer composite materials. Because this is just a proof that if the engine is strong enough to send that thing hurtling through the fucking air, it doesn't matter what it's made out of. Holy shit, you got enough thrust. Shit, man, you can make anything go airborne. With enough thrust, you can fly a fucking brick. You can literally fly a brick. You just have to have enough thrust. To control costs, Lockheed used a more easily worked titanium alloy which softened at a lower temperature. The challenges posed led Lockheed to develop new fabrication methods, which have since been used in the manufacture of other aircraft. Lockheed found that washing welded titanium requires distilled water, as the chlorine present in tap water is corrosive. Cadmium-plated tools could not be used as they also caused corrosion. Metallurgical contamination was another problem. At one point, 80% of the delivered titanium for manufacture was rejected. Damn. Shit. Rejected. The high temperatures generated in flight required special design and operating techniques. Major sections of the skin of the inboard wings were corrugated, not smooth. Aerodynamics initially opposed the concept, disparagingly referring to the aircraft as Mach 3 variant of the 1920s era Ford trimotor, which was known for its corrugated aluminum skin. But high heat would have caused the smooth skin to split or curl, whereas the corrugated skin could expand vertically and horizontally and had increased longitudinal strength. Fuselage panels were manufactured to fit only loosely with the aircraft on the ground. Proper alignment was achieved as the airframe heated up, with thermal expansion of several inches. Because of this, and the lack of a fuel sealing system that could remain leak-free with the extreme temperature cycles during flight, the aircraft leaked JP-7 fuel on the ground prior to takeoff, annoying ground crews all over. Because they were the ones that had to clean the shit up. The pilot gets to have all the fun. Meanwhile, there's dudes scrubbing the runway. Damn it. Not literally, nobody was out there actually like on their hands and knees fucking scrubbing the runway. The outer windscreen of the cockpit was made of quartz and was fused ultrasonically to the titanium frame. The outer windscreen of the cockpit was made of quartz and was fused ultrasonically to the titanium frame. That's fucking crazy. The temperature of the exterior of the windscreen reached 600 degrees Fahrenheit during a mission, or 316 degrees Celsius. Some SR71 had red lines painted on the upper surface of the wings to show no step areas, which included the trailing edge and the thin, fragile skin where the inner wing blended to the fuselage. This portion of the skin was only supported by widely spaced structural ribs. Yup, gotta allow for that expansion. Damn, that thing looks so sick. The Blackbird's tires, manufactured by B.F. Goodrich, contained aluminum and were inflated with nitrogen. They cost $2,300 each and generally required replacing within 20 missions. The Blackbird landed at more than 170 knots and deployed a drag parachute to reduce the landing roll and brake and tire wear. Titanium was in a short supply in the United States, so the Skunkworks team was forced to look elsewhere for the metal. Much of the needed material came from the Soviet Union. Ha-ha! Ho-ho! That's actually kind of funny. Buying the materials you need to spy on the enemy from the enemy. All right. Colonel Rich Graham, SR71 pilot, described the acquisition process. At some point on Battle Tactics and War Strategies, we will go over the Cold War, and we will be going back over this very specific point in a little bit more detail about the purchase of titanium from the USSR to spy on the USSR. Like, what the fuck? Talk about tactical genius, man. I'm telling you. If you take their resources, then they don't have the resources. How the USSR didn't like... we'll get into that on Battle Tactics and War Strategies. This is fucking airplanes. We're talking about airplanes. The airplane is 92% titanium inside and out. Back when they were building the airplane, the United States didn't have the ore supplies. An ore called root tail ore is a very sandy oil, and it's only found in very few parts of the world. The major supplier of the ore was the USSR. Working through the third world countries and bogus operations, they were able to get the root tail ore shipped to the United States to build the SR71. Again, we'll go into more detail on that when I cover the fucking Cold War and Battle Tactics and War Strategies. However, the second operational aircraft designed around a stealth aircraft shape and materials following the Lockheed A-12, the SR-71, had several features designed to reduce its radar signature. The SR-71 had a radar cross-section of around 110 square feet, or 10 meters squared, drawing on early studies in radar stealth technology, which indicated that a shape with a flattened, tapering sides would reflect most of the energy away from the radar's beam place of origin. Engineers added chines and canted the vertical control surfaces inward. Special radar-absorbing materials were incorporated into sawtooth-shaped sections of the aircraft's skin. Cesium-based fuel additives were used to somewhat reduce the visibility of exhaust plumes to the radar, although exhaust streams remained quite apparent. Yeah, we'll see that in a second. Johnson later conceded that Soviet radar technology advanced faster than stealth technology employed against it. Let's have a little bit of fun, shall we? Well, the SR-71 carried radar countermeasures to evade interception efforts. Its greatest protection was the combination of high altitude and very high speed, which made it invulnerable at the time. Along with its low radar cross-section, these qualities gave a very short time for an enemy surface-to-air missile, or SAM-site, to acquire and track the aircraft on radar. By the time the SAM-site could track the SR-71, it was often too late to launch a SAM, and the SR-71 would be out of range before the SAM could catch up to it. If the SAM sight could track the SR71 and fire a SAM in time, the SAM would expend nearly all of the delta V of its boost and sustainer phases just reaching the SR71's altitude. At this point, out of thrust, it could do little more than follow its ballistic arc. Dang! Merely accelerating would typically be enough for SR71 to evade a SAM. Changes by the pilots in the SR71's speed, altitude, and heading were also often enough to spoil any radar lock on the plane by SAM sites or enemy fighters. At sustained speeds of more than Mach 3.2, the plane was faster than the Soviet Union's fastest interceptor, the Mikoyan Gurevich MiG-25, which also could not reach the SR-71's altitude. Just throwing that fuck out there. During its service life, no SR-71 was ever shot down. The SR-71 features chines, a pair of sharp edges leading aft from either side of the nose along the fuselage. These were not a feature in the early A3 design. Frank Rogers, a doctor at the Scientific Engineering Institute, a CIA front organization, discovered that a cross-section of sphere had a greatly reduced radar reflection, and adapted the cylindrical-shaped fuselage by stretching out the sides of the fuselage. After the advisory panel provisionally selected Convair's fish design over the A3 on the basics of RCS, Lockheed adopted chines for its A4 through A6 designs. Aerodynamicists discovered that the chines generated powerful vortices and created additional lift, leading to unexpected aerodynamic performance improvements. Angle of incidence and the delta wings could be reduced for greater stability and less drag at high speeds, allowing for more weight to be carried, such as fuel. Landing speeds were also reduced, as the chines vortices created turbulent flow over the wings at high angles of attack, making it harder to stall. The chines also acted like the leading edge extensions, which increased the agility of fighters such as the F-5, F-16, F-A-18, MiG-29, and Su-27. The addition of chines also allowed the removal of the planned canard foreplanes. Let's fucking go, buddy. The same power plant was used for the A-12, YF-12, and SR-71. It consists of three main parts: the inlet, J-58 engine, and its nacelle, and ejector nozzle. All three have an important influence on the overall installed performance of the propulsion system. Typical for any supersonic power plant, the engine cannot be considered separate from the rest of the power plant. Rather, it may be regarded as the heat pump in the overall system of inlet, the engine, and nozzle. The net thrust available to propel the aircraft may be a large extent controlled by performance of the inlet and nozzle rather than the physical potentialities of the engine alone. This illustrated for the Blackbird by the thrust contributions from each component at Mach 3+, with maximum afterburner, inlet 54%, engine 17.6%, ejector nozzle 28.4%. When stationary at low speeds, the inlet caused a loss in engine thrust. This was due to the flow restriction through the inlet when stationary. Thrust was recovered with ram pressure as flight speed increased. Uninstalled thrust, 34,000 pounds. Installed at zero airspeed, 25,500 pounds, rising through 30,000 pounds at 210 knots. Unstick speed. At supersonic speeds, not all the airflow approaching the inlet capture area entered the inlet. At supersonic speeds, an intake always adapts to the engine requirements rather than forcing air into the engine, and the unwanted air flows around the outside of the cowl, causing spillage drag. More than half the air approaching the capture area had to be spilled at low supersonic speeds, and the amount reduced as the design speed was approached, because the inlet airflow had been designed to match the engine demand at that speed and the chosen design point ambient temperature. At this speed, the spike shock touched the cowl tip and there was minimal spillage, as shown by Campbell. The inlet and engine matching was also shown by Brown, who emphasized the benefit of increased engine airflow at higher Mach numbers that came with the introduction of bleed bypass cycle. These two authors show the disparity between inlet and engine for the Blackbird in terms of airflow, and it's further explained in more general terms by Oates. Engine operation was adversely affected when operating behind an unstarted inlet. In this condition, the inlet behaved like a subsonic inlet design at high supersonic speeds with very low airflow to the engine. Fuel was automatically diverted by a fuel derrick system from the combustor to prevent turbine over temperature. All three parts were linked by the secondary airflow. The inlet needed the boundary layers removed from its spike and cowl surfaces. One with the higher pressure recovery, the cowl shop track bleed, was chosen as a secondary air to ventilate and cool the outside of the engine. It was assisted from the inlet by pumping action of the engine exhaust in the ejector nozzle, cushioning the engine exhaust as it expanded over a wide range of pressure ratios, which increased with flight speed. Mach 3.2 in a standard day atmosphere was the design point for the aircraft. However, in practice, the SR71 was more efficient at even faster speeds and colder temperatures. The specific range chart showed for a standard day temperature and a particular weight that Mach 3.0 cruise used at 38,000 pounds per hour of fuel. At 3.15 Mach, the fuel flow was 36,000 pounds per hour. Yeah, the faster you go, the better the fucking fuel economy. Flying in colder temperatures, known as temperature deviations from the standard day, would also reduce fuel used. During one mission, the SR71 pilot Brian Shaw flew faster than usual to avoid multiple interception attempts. It was discovered after the flight that this had reduced the fuel consumption. It is possible to match the power plant for optimum performance at only one ambient temperature because the airflows for supersonic inlet and engine vary differently with the ambient temperature. For an inlet, the airflow varies inversely with the square root of the temperature, and for the engine, it varies with the direct inverse. The inlet needed internal supersonic diffusion, since external compression used on slower aircraft caused too high a drag at Blackbird speeds. The aerodynamic features and functioning of the inlet are subject of a patent. Supersonic inlet for jet engines by the inlet designer David Campbell. When operating as an efficient supersonic compressor, supersonic diffusion takes place in front of the cowl and internally in a converging passage as far as the terminal shock, where the passage area starts increasing and subsonic diffusion takes place. The inlet may also operate very inefficiently if the terminal shock is not held in a position by the control system. In this instance, if the shock moves forward of the minimum area, the throat, it will be in an unstable position and shoots forward in an instant to stable position outside the cowl, known as unstarted. The features of the inlet and what they do are also explained in the A-12 Utility Flight Manual and in a presentation by Lockheed Technical Fellow Emeritus Tom Anderson. All features are visible in varying degrees in center body or spike and fully forward position, spike boundary layer bleed slots where normal shock is located, cowl boundary layer bleed shock trap entrance, streamlined bodies known as mice in subsonic flow, forward bypass bleed ports between each of the mice, rear bypass ring, louvres on the external surface of the spike boundary layer overboard, louvers on the external surface for the front bypass overboard. Those are all the features that are visible in varying degrees, I guess. Venting this bypass overboard could affect the aircraft flying qualities because it produces high drag, 6,000 pounds at cruise with 50% door opening, compared to the total aircraft drag of 14,000 pounds. In early years of operation, the analog computers would not always keep up with the rapidly changing inputs from the nose boom. If the duct back pressure became too great and the spike was incorrectly positioned, the shock wave would suddenly blow out the front of the inlet, causing an inlet unstart. During unstarts, the afterburner extinctions were common. The remaining engine's asymmetrical thrust would cause the aircraft to yaw violently to one side. SAS autopilot and manual control inputs would attempt to regain controlled flight, but often extreme yaw would reduce airflow in the opposite engine and stimulate sympathetic stalls. This generated a rapid counter-yawing and often coupled with loud banging noises and rough ride, during which the crew's helmets would sometimes strike their cockpit canopies. Holy shit. Did you imagine just like the equivalent of hitting a fucking curb in the sky? Like, what the fuck? One response to a single unstart was unstarting both inlets to prevent yawing, then restarting them both. Well, that's a fucking solution. After wind tunnel testing and computer modeling by NASA Dryden Test Center, Lockheed installed an electronic control to detect unstart conditions and perform this reset action without pilot intervention. During troubleshooting of the unstart issue, NASA also discovered the vortices from the nose chines were entering the engine and interfering with engine efficiency. NASA developed a computer to control the engine bypass doors, which countered this issue and improved efficiency. Beginning in 1980, the analog inlet control system was replaced by a digital system, digital automatic flight, and inlet control systems, which reduced unstart instances. Fucking legends. The engine was an extensively redesigned version of the J58P2, an existing supersonic engine which had run 700 development hours in support of proposals to power various aircraft for the U.S. Navy. Only the compressor and turbine aerodynamics were retained. New design requirements for cruise at Mach 3.2 included operating with a minimum high ram temperature of 800 degrees Fahrenheit entering the compressor, a continuous turbine temperature capability of 450 degrees Fahrenheit hotter than previous experience, continuous use of maximum afterburning, and the use of new, more expensive materials and fluids required to withstand the unprecedented high temperatures. The engine was an afterburning turbojet for takeoff and transonic flight, and a low bypass augmented turbofan for supersonic acceleration. It approximated a ramjet during high-speed supersonic cruise. It was a low bypass turbofan for subsonic loiter. Analysis of the J58P2 supersonic performance showed the high compressor inlet temperature would have caused stalling, choking, and blade breakages in the compressor as a result of operating at low corrected speeds on the compressor map. These problems were resolved by Pratt & Whitney engineer Robert Abernathy and were explained in his patent Recover Bleed Air Turbojet. His solution was to 1. Incorporate 6 bleed air tubes prominent on the outside of the engine to transfer 20% of the compressor air to the afterburner, and so basically fucking turbo. And 2. Modify the inlet guide vanes with a 2-position trailing edge flap. The compressor bleed enabled the compressor to operate more efficiently, and with the resulting increase in engine airflow matched the inlet design flow with an installed thrust of 47%. A continuous turbine temperature of 2,000 degrees Fahrenheit was enabled with air-cooled first-stage turbine vane and blades. Continuous operation of maximum afterburning was enabled by passing relatively cool air from the compressor along the inner surface of the duct and nozzle. Ceramic thermal barrier coatings were also used. The secondary airflow through the nacelle comes from the cowl boundary layer bleed system, which is oversized to give a high enough pressure recovery to support the ejector pumping action. Additional air comes from the rear bypass doors and, for low-speed operation with negligible inlet ram, from suck-in doors by the compressor case. The ejector nozzle had to operate efficiently over a wide range of pressure ratios from low, with no inlet ram, with stationary aircraft, to 31 times the external pressure at 80,000 feet. A blow-in door ejector nozzle had been invented by Pratt & Whitney engineer Stuart Hamilton in the late 1950s and described in his patent variable area exhaust nozzle. In the description, the nozzle was an integral part of the engine, as it was in contemporary Mach 3 General Electric YJ93. For the Blackbird power plant, the nozzle was more efficient structurally. It was lighter by incorporating it as a part of the airframe because it carried fin and wing loads through the ejector shroud. The nozzle used secondary air from two sources: the inlet cowl boundary layer and the rear bypass from immediately in front of the compressor. It used the external flow on the nacelle through the tertiary blow-in doors until ram closed them at Mach 1.5. Only secondary air was used at higher speeds with the blow-in doors closed. At low flight speeds, the engine exhaust pressure at primary nozzle exit was greater than ambient, so tended to overexpand to lower than ambient in the shroud, causing impingement shocks. The secondary and blow-in door air surrounding the exhaust cushioned it, preventing overexpansion. Inlet ram pressure increased with flight speed, and higher pressure in the exhaust system closed. First the blow-in doors, and then started to open the nozzle flaps until they were fully open at Mach 2.4. The final nozzle area did not increase with further increase in flight speed, because its external diameter, greater than the nacelle diameter, would cause too much drag. JP7 fuel was used. It was difficult to ignite to start the engines. Triethylborane, which ignites on contact with air, was injected to produce temperatures high enough to ignite the JP7. The TEB produced a characteristic green flame which could often be seen during engine ignition. The fuel was used as a heat sink for the rest of the aircraft to cool the pilot and electronics. As an electric starting system was not possible due to limited capacity of cooling system, so the chemical ignition system was used. Northrop Corporation's Electronics Development Division had developed an inertial guidance system, or ANS, which could correct inertial navigation system errors with celestial observations. For the SM-62 Snark missile, and a separate system for the ill-fated AGM-48 Skybolt missile, the latter of which was adapted for the SR71. Before takeoff, a preliminary alignment brought the ANS's inertial components to a high degree of accuracy. In flight, the ANS, which sat behind the reconnaissance systems officer's RSO position, tracked stars through a circular quartz glass window on the upper fuselage. Its blue light source star tracker, which could see stars during both day and night, would continuously track a variety of stars as the aircraft's changing position brought them into view. The system's digital computer ephemeris contained data on a list of stars used for celestial navigation. The list first included 56 stars and was later expanded to 61. ANS could supply altitude and position to flight controls and other systems, including the mission data recorder, automatic navigation to preset destination points, automatic pointing and control of cameras and sensors, and optical or SLR sighting of fixed points loaded into the ANS before takeoff. According to Richard Graham, a former SR71 pilot, the navigation system was good enough to limit drift to 1,000 feet, or 300 meters, off the direction of travel at Mach 3. And getting closer to the end here with this. Talk about some of the sensors and shit. The SR71 here we go with the long-winded fucking names. I'll guarantee it, when it comes to aircraft sensors and fucking equipment, it's gonna be the long-winded ass names. Let's go. SR71 originally included optical infrared imagery systems, side-looking airborne radar, or SLAR, electronic intelligence gathering systems, defense systems for countering missiles and airborne fighters, and recorders for SLAR and ELINT, and maintenance data. The SR71 carried a Fairchild tracking camera and an infrared camera, both of which ran during the entire mission. Yeah, that same Fairchild tracking cameras on the fucking A-10. As the SR-71 had a second cockpit behind the pilot for the RSO, it could not carry the A-12's principal sensor, a single large focal-length optical camera that sat in the Q bay behind the A-12's single cockpit. Instead, the SR-71's camera systems could be located either in the fuselage chines or the removable nose chine section. Wide area imaging was provided by two of iTech's operational objective cameras, which provided stereo imagery across the width of the flight track, or an iTech optical bar camera, which gave the continuous horizon-to-horizon coverage. A closer view of the target area was given by the Hikon technical objective camera, which could be directed up to 45 degrees left or right of the center line. Initially, the TEOCs, or Hikon Technical Objective Camera, could not match the resolution of the A-12's larger camera, but rapid improvements in both the camera and film improved its performance. SLAR, built by Goodyear Aerospace, gotta love the blimps, could be carried in the removable nose. In later life, the radar was replaced by Loral's advanced synthetic aperture radar system. There we go, there's a longer name. Both of the first SLAR and ASARS-1 were the SLAR and ASARS-1 were ground mapping imaging systems collecting data either in fixed swaths left or right of the center line or from a spot location for higher resolution. ELINT gathering systems, called the Electromagnetic Reconnaissance System, built by AIL, could be carried in the chine bays to analyze electronic signal fields by being passed through, and were programmed to identify items of interest. Over its operational life, the Blackbird carried various electronic countermeasures, including warning and active electronic systems built by several ECM companies, and called systems A, A2, A2C, B, C, C2, E, G, H, and M. On a given mission, an aircraft carried several of these frequency-purpose payloads to meet the expected threats. Major Jerry Crew, an RSO, told the Air and Space Smithsonian that he used a jammer to try to confuse surface air missile sites as their crews tracked his airplane, but once his threat warning receiver told him a missile had been launched, he switched off the jammer to prevent missile from homing in on its signal. After landing, information from the SLAR and ELINT gathering systems and the maintenance data recorder were subjected to post-flight ground analysis. In the later years of its operational life, a data link system could send ASARS-1 and ELINT data from about 2,000 miles, or nautical miles, rather than miles, nautical miles, of track coverage to suitably equipped ground station. And finally, to bring it all home, obviously had to keep the pilots alive way the fuck up at 80,000 feet. So you had to have some kind of life support system. Flying at 80,000 feet meant the crews could not use standard masks, which could not provide enough oxygen above 43,000 feet. Specialized protective pressurized suits were produced for the crew members by David Clark Company for the A-12, the YF-12, M21, and SR71. They were basically fucking spacesuits. Furthermore, an emergency ejection at Mach 3.2 would subject crews to temperatures of about 450 degrees Fahrenheit. Thus, during a high-altitude ejection scenario, an onboard oxygen supply would keep the suit pressurized during the descent. The cockpit could be pressurized to an altitude of 10,000 or 26,000 feet during flight. The cabin needed a heavy-duty cooling system, as cruising at Mach 3.2 would heat the aircraft's external surface well beyond 500 degrees Fahrenheit, and the inside of the windshield to 250 degrees Fahrenheit, turning the cockpit into a fucking heater. Jeez, you're just in an oven in there. 250 degrees, you'd be cooking. An air conditioner used a heat exchanger to dump heat from the cockpit into the fuel prior to combustion. The same air conditioning system was also used to keep the front nose landing gear bay cool, thereby eliminating the need for special aluminum impregnated tires, similar to those used on the main landing gear. Blackbird pilots and RSOs were provided with food and drink for the long reconnaissance flights. Water bottles had long straws which crew members guided into an opening in the helmet by looking in a mirror. Food was contained in sealed containers similar to toothpaste tubes, which delivered food to crew members' mouth through the helmet opening. Fucking wild, dude. What the hell? That is fucking crazy, buddy. Fucking crazy. That is it, though. That is all the content I had today for the SR71 Blackbird. I think I did a pretty good job at covering a good portion of the relevant information about the plane, its design, and some of the systems within it. Right? A little bit of the background, too. We did a little bit of the history, a little bit of the background. But that being said, that concludes today's episode of Aviation Prattle. We'll see if I come back and fucking stream for some gaming. I don't know, there's some thunderstorms going on around the area, so might lose power, might not lose power. I don't know, we'll fucking see what's happening. Either way, that being fucking said, get off of that screen real quick, bring myself back up. That being said, I hope you all have a wonderful morning, afternoon, evening, or night, wherever you're at in the world. Enjoy your time, because it may be limited. You never know. You might install an ejector seat in your car, and it doesn't work the way it should, and that guardrail comes a little bit too fast. Now, while that's a very low possibility, it still is one nonetheless, so you should enjoy your time. Enjoy it all, regardless of the situation, Because everything is a matter of perspective, and you can choose how to interact with any situation however way you want to choose to. It's up to you. The choice is yours. Personally, I would hope that you choose to enjoy whatever the fuck you're doing, as we don't live very fucking long. But my time with you this evening has come to an end. I might be back in 20, 30 minutes or so. I might not. We'll see what's going on. That being said, I will catch y'all next Thursday for the Aviation Prattle. Next, let's see, Saturday. No, this upcoming Saturday for fucking gaming shit. Monday for some more samurai shit. Tuesday and Wednesday for some fucking Ottoman-Hungarian wars. And then Halloween, fucking awesome, is going to be Vlad the Impaler. Got a bunch of shit coming up. Get ready for it. Hit that subscribe, hit that like. Join in on the fray. Hop in the chat, say what's up, do your thing. That being said, I am the fuck out of here, y'all. Have a good one.